Welcome to our talk in CIRPe2020 Global Web Conference on flexible mass customization. My name is Akash Verma and I'm a PhD student at K11 Belgium. Along with me is another speaker, Jarne Machiels, who is a researcher at Hasselt University in Belgium. The title of our paper and talk is Printed Electronics as an Enabling Technology to Realize Flexible Mass Customized Smart Applications. The outline of this talk is I will introduce you to the printed electronics and its application, and how it is different from conventional electronics, and how we can realize smart, flexible, mass customized products by using these techniques. Then we will talk about problem statement and what are the motivations for this work. Along with it, we'll discuss about the state of the art in RFID technologies. For this work, we have chosen aerosol jet printing and screen printing. Printed electronics is an additive deposition of any functional materials on different substrates via different printing processes to realize electronic devices, circuits, and interconnects. It's a multidisciplinary approach with a market value of more than $30 billion. The four fundamental pillars of printed electronics are inks, substrates, printing methods, and sintering. The details of it you can see in this image. There are several applications of printed electronics, which ranges from industries like biomedical, photovoltaics, energy harvesting, lightings, even telecom, smart packaging, and printed sensors. The imagination is our limitation. From the figure, we can see that from figure A and B, it's a flexible display printed on a transparent foil which is attached to a skin. Also, from figure C and D, we can see it's a silver printed tracks printed on a stretchable substrate. In figure E, we can see that it's a printed circuit which is embedded on an object which was produced by FDM technique. Figure F shows that conductive tracks can be also printed on free-form substrates like PCABS in this case, which was produced by injection molding. How it is different from conventional electronics? You can see that from the table that printed electronics have advantages over conventional electronics. But the biggest advantage is the form factor, which is a great asset in printed electronics, which means the ability to manufacture flexible, bendable, or even stretchable devices with customization. But there are some disadvantages like scalability, yield, and resolution, but the research has been going on to improve these factors. Now I will give it to Jarne.
The variety of printing techniques allows flexible mass customization for each specific application. Well, as you can see, a lot of conventional printing methods can be used in the field of printed electronics. They all have their own characteristics regarding printing speed, print thickness, resolution, and so on. Depending on a lot of parameters and the application itself, the use of printing methods allows to scale up thanks to the ability of roll-to-roll printing. So, the problem statement of our research is the fact that the study of high-frequency RFID NFC printed antennas on paper substrates is just limited. If you have a look into the field of aerosol jet printed antennas, almost no studies are available. So, we selected this application of a printed antenna as an example of printed electronics, and we would like to showcase the ability of HEP as a rapid prototyping technique, and we would like to use screen printing for mass customized manufacturing of these antennas. So that at the end we can conclude that printed electronics is an enabling technology to realize flexible mass customized smart applications. So before that, I would quickly explain how this RFID technology works. An RFID system exploits electromagnetic waves to transfer data wirelessly. This two-way data transferring method consists of a transponder or tag which is located on the object to be identified and a reader to communicate between the tag and user software. Based on the energy supply, active and passive tags are distinguished. Active tags always use their own energy supply, like a battery, while passive systems directly harvest power from the radioelectric energy of the reader. The tags can also be divided by their working frequency, which is related to the read distance. But in our research, we focus on printing passive high-frequency RFID antennas with a short read range and working frequency of 13.56 MHz. Now, I would just quickly show some state-of-the-art applications of printed RFID antennas. Both references show a dipole antenna at 868 MHz working frequency, screen printed with a conductive silver ink on a cardboard substrate. The first demo has even some sensing capabilities as a force sensor and opening detector. If we just have a look to high-frequency RFID antennas, Lee et al. Were able to print a functional antenna on a thick-coated photo paper by screen printing a silver ink. In this research, we investigated 4 different loop antenna designs, and they all differ in the number of coils and the width of the tracks, which have an influence on the electrical properties, such as the series resistance, which should be below 50 ohm, and the inductance, which should be around 3 micron. To functionalize the printed antennas, 3 characterization steps are performed. Firstly, the printed antennas are characterized by some basic electrical measurements to check the print quality. In the next step, RF performance measurements are performed to check the functionality of the printed antenna. And finally, the RFID functioning is tested by trying to extract the integrated text code. Right now, I give the word to Akash to present the results of the Aerosol Jet printed antennas.
Aerosol jet printing is a mass-class mesoscale multi-material deposition technique. It's based on direct writing, non-contact based methodology. The feature size of the printed deposited pattern ranges from 10 microns to millimeter, whereas the layer thickness ranges from hundreds of nanometer to tens of microns. It has ability to use all broad range of ink viscosities from 1 to 1000 megapascal seconds. One of the unique features of aerosol jet printing is the standoff distance, which ranges from 1 to 5 millimeters, which makes it possible to print on literally any freeform substrates. Like on the figure right side, we can see a printed circuit has been printed on a table tennis curved ball. Aerosol jet printing is divided into 2 different kinds of atomization techniques, ultrasonic and pneumatic. The basic working principle of ultrasonic atomization can be explained from this figure on the right side. There are 5 major points. The first one is atomization, which means a liquid suspension ink can be atomized into aerosol particles, which is then transported towards the printhead using a nitrogen gas. In the third step of collimation, a sheath gas is introduced to collimate and align the particles in the same way, which helps to aerodynamically focus all the particles towards the printhead. In the last step, the aerosolized ink particles leave the nozzle and impact on the substrate in a desired pattern. In this work, we have used Novacentrix silver nanoparticle ink with a viscosity of 20 centipoise, with a sheet resistance of less than 25 milliohms per square. The 4 different substrates were used. The 2 are paper-based, which are PE Smart Type Paper 2 and Algobarus. The other are standard PET foil and FR4 board. Thermal sintering was done at 120 minutes for 120 degrees Celsius in a thermal oven. From the right side, we can see a high quality print of all the printed antennas with no overspray and no short circuits. Regarding the performance and functionality testing of printed antennas, which are produced by aerosol jet printing, we can see the resistance and the inductance are within the range and fulfill the criteria of a functional antenna as described before. From the frequency curve, we can see the resonating frequency is 14.13 megahertz. Apart from that, we can see there is a slight frequency shift with a wider bandwidth. This is caused by high resistance. but it showcased that aerosol jet printing can be used as a rapid prototyping technique for functional RFID antennas. The next step is screen printing of mass production, which will be explained by Jarne.
Well, screen printing is a direct contact printing technique, transferring an ink onto a substrate by using a mesh screen. The screen printing process consists of two different steps. First of all, the squeegee, which is a rubber blade, is moved across the screen, thereby filling the mesh openings with ink. In this forward movement, the screen is momentarily forced to the substrate, and the ink is deposited by capillary forces. In the second step, the blade scrapes the ink axis to its initial position, and the printing process can be repeated. The main print parameters include the screen dimensions, the squeegee parameters, printing speed, snap-off distance, and so on. In general, screen printing uses high viscous thixotropic inks, and for example in the field of printed electronics, metal inks, polymer inks, carbon inks, or even dielectric inks are used. To screen print a high-frequency RFID antenna, we decided to test two different highly conductive nanosilver inks. The Orecon CIRPe2020 from Agfa-Gewert and the Loctite ECI 1011 from Henkel. As post-printing step, both inks should be cured for 10 minutes at 150 degrees Celsius. The paper substrates that we used in this research were PE Smart Paper Type 2 from Felix Schuller, which is a paper substrate with a thick coating layer specifically developed for printed electronics, and Alcobares from CIRPe, which is a standard label material. In a first experiment, we tested the functionality of the 4 different antenna designs by printing all of them with both conductor silver inks on the PE Smart Paper Type 2. The results of this test show clearly that the L11 and L18 design did not generate functional antennas, in contrast to the other two designs. Especially the L6 design looked very promising for printed high-frequency RFID antennas, and for that reason we selected this design for further investigation. A second experiment, the L6 antenna was screen printed with both silver inks on the standard label material Alcobares. The functionality test showed that the antennas printed with the Orecon ink were not functional. The inductance of 2.13 microhenry was too low. In contrast, the antennas printed with the Loctite ink were all functional with an inductance value around 3 microhenry. So, it can be concluded that the combination of the Loctite ink, the Alcobares substrate, and the L6 antenna design is successful to manufacture flexible, customized, functional high-frequency RFID antennas. And because the screen printing technique was used, it is quite easy to scale up to mass production. To conclude, the potential of aerosol jet printing as a rapid prototyping method for antenna manufacturing was showcased. In addition, the screen printing technique was successfully used for flexible mass customization in the field of antenna manufacturing. This research infers that printing techniques can be used as production method of functional flexible antennas for high-frequency RFID applications. It also implies that printed electronics can be an enabling technology for the development and manufacturing of several flexible mass-customized electronic applications and devices. The last thing left for me is to thank all of our research and industrial partners, and of course the different funding agencies of the 3D Electroprint and Paperonics project. I would also like to thank all of you for your attention. If you still have any questions, please feel free to ask them or to contact us by email.